Welcome along once again to Enfield Physics Tutor. We are surrounded by waves, and today we're going to take a look at a simple example of two identical pulses interfering and build upon that and have our minds blown as you think about what happens when you go to see your favourite band play. A typical A-level question might say something like, describe what happens when identical wave peaks moving in opposite directions meet. And this will be your cue to write a short passage including words like superpose, constructive, interference and maybe even amplitude. To make life as easy as possible, and let's face it, who doesn't want to do that, we will assume that these pulses are identical parts of a sine wave travelling in opposite directions. This is a hugely simplified version of exactly what you might find on a guitar string. I created this model using Excel, and I'm not really going to say much about how, except that there must be easier ways to do it. First, you can see the blue pulse moving from left to right. It's just the positive section of a sine wave. Now observe the orange version going the other way. Thirdly, we put both waves on the graph together and watch them moving together, through each other and back out the other side. Whilst you're watching this, have a think about what you reckon the addition of these two pulses is actually going to look like. Now I know that in all likelihood you already know what the answer to that question is, but do you really? One thing about all this wave interference stuff is that it's far more complex in reality than just two little peaks bouncing along a string. Interference is going on all around you. Just imagine 30 kids sitting in a class and one teacher, and these kids are good little kids and they're totally silent. As the teacher is talking, their sound waves are bouncing off all four of the walls, the ceiling, the floor, plus all the different desks, maybe off even some of the kids' heads. So you've got multiple sources and reflections of his or her voice bouncing around that room and interfering. Now just imagine the chaos, as it were, if those 30 kids all decide to talk at the same time. Innumerable waves all interfering. That's going to create some complex resultant wave patterns. I think it's important to grasp that this thing gets really complex, otherwise it kind of makes it hard to understand what's going on in the models. Now it's time to look at how these peaks add together as they superpose. We've kind of ignored it up till this point. And you can see this in the grey line at the top of my rather splendid animation. As you can see, I'm looping the waves so the pulses are going backwards and forwards along the string. Watch carefully what happens as the pulses move through each other. Earlier on I asked you to guess the shape, and on one level I know you got this right because you've been told over and over again that when the two pulses are on top of each other, you get a maximum amplitude, and of course that's true. But if you look carefully, you can see that what's going on at points where the waves are superimposed but are not exactly with the two peaks on top of each other, that the resultant wave, the grey wave, is actually much more complicated. It's not just a simple sine wave, or part of a sine wave I should say, as perhaps you might have thought. Here's the first of a few screenshots I've taken of my animation. And in this one you can see that the orange and blue waves are just beginning to overlap. Notice how in the grey, the combination of the two waves, it's not a simple shape anymore. Although it is symmetrical, you couldn't say that it is a simple part of a sine or a cosine wave. So we have two peaks, and then in between them we have like a dip, but it's not a dip that extends all the way down to the zero displacement point again. In this second one you can see that the orange and blue waves are now a little bit more superposed, and the shape has changed. The slight indentation in the middle point has now moved up to become a maximum. So you could describe this as like maybe three little peaks, or you could say it looks a bit like a wobbly jelly. As you can see, it's becoming a complex shape. As the two waves sit on top of each other, we find ourselves arriving at long last at our much loved and simple single peak as the two waves add together, which of course, as you know, has the same shape but twice the amplitude as the original pulses. So even when you combine two identical simple peaks together, the result is much more complex, albeit predictable. Now imagine what it's like when you go and see your favourite band play. The complexity of the waves plus the interference they create as they pass through each other is just truly mind-blowing. And our ears and brains just decode all that sweet sound in what feels like an instant. You don't need to be able to reproduce these shapes, but do be aware of them. They'll really help us to understand what happens when we move on to the next video where we discuss where do those standing waves actually come from?